All right, welcome everyone. So I guess we'll get started. The agenda for today is very simple. We're going to just work on the exercise that we left in the last week on Wilson adjusted proportions and talk about some chi-square test. Just to remind you, we have a quiz, we have an exam coming up on April 2nd, that's Thursday. So you'll get a paper, as you'll get your questions on the morning of Thursday, and it's due Friday morning. But before I get started, any questions about exam, anything that's not clear in the class, any other pressing questions?
Are you going to have another like review sheet like you did for the last exam?
Yes, I will have a review sheet. I should have uploaded actually. Yeah, thanks for reminding me actually. I'll have a review sheet posted. Yes.
Thank you.
Yeah. Any other questions? Okay, all right. So I'm going to switch off my video because my machine doesn't like both the things at once. It was overheating last time, so I'll try to avoid it. I'm going to share my screen. Okay. Let's go back. Okay. All right. So where we left off in the last week was essentially on this problem. We were given that there's a public opinion poll conducted, and there were 1,000 people, of which we randomly chose 1,000 people, which were randomly chosen. And around 637 of them answered that they're going to trust the president. So the first problem essentially asks us as to what the true proportion would be, right? And looking at this problem, the first thing that you would say is that, I'm already given this proportion. And that proportion is going to be 637 by 1,000. But that proportion is slightly problematic because it's asking for, in some sense, this is asking for a true proportion, right? So the math behind this is very simple. What we say is if I want to estimate a true proportion, then I'm going to essentially make it look like it's going towards 0.5. And the way to do that is by adding 2 on the numerator and 4 in the denominator. Okay. And this is essentially called the Wilson adjusted proportion. Okay, it's very simple. And the idea, the reason we are doing this is because in order to estimate, this gives us a better estimate of the confidence interval, okay, which we are going to tackle in the next problem. So that is essentially the motivation behind doing this trick of adding +2 and doing a +4 in the denominator. And if you do that, then your final value comes around to be 0.836. This is 0.636, not 836. Okay. Okay. And the idea is very simple again. So the reason we are doing this is because we want to come up with a better confidence interval, and that confidence interval would not have been possible have we been doing just a plain estimate. Is there any question? Okay, all right. So we'll go to problem B, which is asking us to estimate the 95% confidence interval. And the 95% confidence interval is, for that, we require the standard estimate of the standard error of P bar. And the standard error of P bar is again very similar to what we did earlier. So I will denote this as P hat. So the reason this formula looks like this is because you can think of this as a binomial, as a Bernoulli trial. So it's either, so this is Bernoulli-like, which is essentially, it's either 1 or 0. And if we do that, then this is essentially just plugging in the values. Okay, and n is 1,000. That's already given to you. Okay, so the confidence interval is given by your p tilde plus minus 1.96 standard error of p, and this 1.96 is essentially obtained from your table. So this is kind of kind of a standard thing that we have done many number of times by now. So if you plug in the values, this down to 6066 and 6654. Okay. So the next problem asks us that if it is desired to have a standard error of no greater than 0.01, how many people should be surveyed? Okay, so I'm going to move this here. So in problem C, the idea is that you're already given the error of the estimate of the standard error, and you want to count how many number of people should be surveyed. Okay, so we want the standard error to be less than or equal to this value. Okay, where your p hat is essentially given by 0.6. Okay, 1 second. Let me make sure. Okay. Yeah. So p hat is 0.6066. Sorry, this is 636. And what are we asked is what is going to be your value of n, right? And if you plug in the values, you'll get, so the way to plug in values is very simple. So essentially what you're going to get is n plus 4. So notice what I'm going to do. I'm going to take the square of both the sides, and I'm going to move the denominator to the right? So that is going to be, okay. And after that, you just have to plug in the values. And if you plug in the values, this will come around when rounded to be around 2312. Okay, so just to be a bit more explicit, let me write this down to be 231.504. Okay, so this is a floating value, right? This is not an integer. So just to be sure, we are, if we subtract 4 from both sides, we get 2311.04. But we are going to take the approach of upper bounding it. So we are going to take the upper bound, which is going to be 2312. Okay, so you essentially take a ceiling of the value because we want a whole number there. Similarly, for problem D, and problem D is, let me hide this because this is, so in problem D, you're essentially asked is the estimate of the proportion is not available, and you still desire standard error of going to be less than 0.01. So how many people should be surveyed? So what is the difference between problem C and problem D, right? So in problem C, we were still using the proportion that was given to us as part of the main problem. In problem D, we are asked that the proportion, if this estimate is no longer available, right? So if the estimate is no longer available, what is still available is what we know about it, right? So we know that we want this error to be we want our standard error to be less than the value for our standard error. Okay, we do not know what is p bar and we do not know what is n. So how do we estimate this? So what would happen if we were to actually plot the distribution of p hat times 1 minus p hat? Okay, so if you plot the distribution of p hat times 1 minus p hat, then it looks like something like this. So it's essentially takes the maximum value at p equal to 0.5, and that value is going to be 1 by 4. Okay, so this is the maximum that you can get from multiplying these two values. Okay, and why do we care about that? Because we want the best estimate for, we want the smallest estimate for n. So if you want this to be the smallest possible n, then you want correspondingly this to be the largest possible value. Okay, and the way this makes sense is because we want, in the worst case, that this ratio of some quantity by some quantity should be less than 0.01. So the denominator, if it's very small, then this entire ratio can be very large. The other way this can be very large is by making the numerator very large, right? So The numerator we are going to take the worst case when the numerator is very large, and then we are going to estimate what is the smallest value of n possible. So if you plug in these values here, then the final, then essentially what you're going to do is just plug in the values for n, and this is going to be, that's that, 0.21. I'll again repeat the same exercise. So this is 1/4 and 100 essentially. Okay, so sorry, this should be, this is 25. So n is going to be greater than or equal to 2496. Okay, any questions? All right. Okay, so we move to problem 2, and problem 2 is a quick introduction of what we do in, we're still doing hypothesis testing, but now we are going to work with what is called categorical data. And the way we do that is, in this particular problem, what was given to us is, there's this assumption, which you have also looked in the class, is that there is a certain, there's a certain hypothesis that because of the a person being famous, and they expect their birthdays to be coming in the next few months, it's, even though they are old or even they're susceptible to death, then they have a lesser chance of actually dying before seeing their birthdays. And that's something which we are going to test. The way we are testing this is we are given actual information from this data source of America's Who's and Who. The table here essentially lists down, for all such famous people, depending on which month their birthday is expected, and when do they actually die, right? So around 90 people end up dying 6 months before their actual birthdays. Around 100 people end up dying 5 months before. 106 people die 5 months after their birthdays. Okay, and what is it that we want to test? So we want to test uh, if there is any correlation between the famous person dying before or after their birthday. Okay, so in the first problem, the problem is very general. So what we are going to test is, we are essentially going to test if the birth information is distributed in these. So these are essentially 12 categories, right? And we want to test if the number of deaths that we see, is there any correlation between the number of deaths that we see in a particular month, and how is it correlated to the birth month itself? Okay. Is the problem clear? Okay, so what is going to be a null, right? So the first problem asks us about the null. So this is problem 1, right? So in problem part A, we are asked what the null is. Okay, and the null is very simple, that there is no relation between birth month and the month of death. Okay. And the alternate is, there is some relation. Okay, and what that sum is, we don't really care about right now, because it could go in either directions. Okay. So how do we go about solving this problem? Any guesses? Any takes on how do we solve this problem? You can use the chat feature if you want. If you don't want to unmute yourself, if you want to unmute yourself, that's also fine. If not, I'll go ahead. Is the problem clear before I proceed? So people are dying because for some reason they're either old or they have some ailments. However, these people are also expecting their birthdays to be celebrated, and these are famous people, so there is a different expectation of their birthdays being celebrated. We want to test if there is any correlation between the month that they die and the expectation of their birth month being the same or before or after. Okay. So given this kind of information, we have 1251 deaths, and they happen over 12 months. So what is our expectation, right? So our expectation is that this is our expectation, right? The null expectation says that there is no relation. So given that there are 1251 deaths happening in 12 months, we expect that in 1 month, we have approximately 1251 divided by 12 deaths, right? So the thing that we're going to do here is where the association comes into picture, right? So we are essentially testing for association. Is there any association? In other words, is there any association between the birth month and the death month? And we have given the amount of information, we have a certain expectation. And this expectation comes in terms of the number of deaths that we expect in 1 month, given around 1250 deaths happen over the entire year. Okay, so how do we test for this association? So the choice of statistic, whenever you look for association, in most cases, your choice of statistic is going to be the chi-square. Okay, and the chi-square is essentially a very simple statistic. Okay, so the chi-square statistics essentially tells you is what is the deviation of the observed value, which is OI, from the expected value, having accounted for the expected value. Okay, so the higher this particular statistic is, that means the observed value is very different from the expected value. And the reason we are essentially dividing by EI is, in some case, we are essentially adjusting for the scale that EI is set in. Okay, so let's try to do this for this particular problem. Okay, and the way we do that is we already know what the expected number of deaths are going to be. So our EI, which is same for all the i's, which is I equal to 1 to 12, is 1251 by 12. Okay, and that comes to be 104.25. So in every month, if your null is true, then you expect around 104 deaths to happen, given that around 1250 deaths are happening over the 12 months. So if we do this, and if we calculate, this is our expectation. So this is what we expect to happen. However, what we are observing is different number of deaths in all these years. Now we want to test if the deviation that we see in the number of deaths, is it different from our expectation? Okay, and these number of deaths, the way they are arranged is they are arranged in these 12 categories. Okay, so let's do that, and we'll not write the entire step. So you do 90, which is essentially your first value. Then you keep summing, just try to remove this. We'll keep summing it to the next value, which is 100 minus 1.4.25 square, and keep doing this. Okay. And if you had access to a calculator, and in most cases, this will be a much simpler problem to solve. This has a lot of values, 12 values. So it might get a bit tricky to calculate if you don't have a calculator. But assuming you have a calculator and the numbers are easy, this value comes around to be 17.192. Okay, so this is your chi-square statistic. But that information by itself is not really useful, because we also need just what we did in case of the t-test. There is something called the degrees of freedom. Okay, the degrees of freedom for a chi-square test is essentially n minus 1. Why? Right? So why? So whenever you're testing for association, you have, let's say, n categories, and these n categories were the 12 months that you had access to, right? Now, once you have access to 11 months and this total here, right, you can infer what's the 12th month already is, right? What is the count associated with the 12 months? So imagine I gave you 1251. I gave you the values for all the months, the number of deaths for all the months except this particular month, right? So you should in principle be able to infer what this value is. And in a hand wavy sense, that's the reason your degrees of freedom are n minus 1. Okay, so in some sense, you're essentially constrained.
You do not have n independent observations. In some sense, you have n minus 1 independent observations. So the DF for this is going to be 11. Okay, so how do we look this up? So for looking this up, we go to a different table now, which is table 9. So we go to table 9. Table 9, again, before we start actually reading the value, we'll read the header of the table, and it says that the values that you see here are non-directional p-values. Okay, and if it's directional, then the p-values are found by dividing the column headings in half. Okay, so our degrees of freedom are 11, and our chi-square statistic is a value which is 17.192. So it's going to occur between these two values. Okay, so our p two-sided is going to be 0.2 to 0.1. Okay. Right, so a p is 0.2 to 0.1. Fine, so that was essentially your problem, and we're going to check if the data is consistent with the null. So what is really happening here, right? So the p-value is definitely going to be between 0.1 and 0.2. So if you take your alpha equal to 0.05 or 0.01 or 0.1, you're essentially going to fail to reject the null, right? And what that essentially means is we are saying that we fail to find any association there is not enough evidence for us to reject the null, which means that we do not find enough evidence to claim that there is possibly an association between the birth month and the death month. Okay. Now, there's another way to actually look at this problem, and that problem is given in part B. So till now, what we were doing was we were concentrating on all the months at once. But if you think about it, probably a better hypothesis to see is, do the people actually die before, right? So here I wrote that the relation here is, the alternate here is sum. But what probably is a better hypothesis in this setting is to check whether more number of people end up dying before their birth month than after, right? Because that would tell us whether we reject the null or not. So if we reorganize our null, which is essentially what the second problem or the part B is asking us to do. So if we reorganize this, to say that the number of deaths, so if we say that we're going to reorganize this and only focus on the before and the after part rather than concentrating on each month. So number of deaths before and after birth month are independent, or in other words, there is no association. So what is the difference between what we were doing in part A and part B? So in part A, we are concentrating on different months altogether and contrasting it with a birth month. In part B, we are now much more focused, and we are saying that the number of death months before and after birth are independent. Okay, so rather than working with two categories, we are now working with 12 categories. We are now working with just two categories, either before. So this is before and this is after. Okay, so everything remains the same, right? And this 560 number that you're seeing here is essentially the summation of all the months in these categories from -6 to -1, and similarly 691. So what really has changed, right? So our expectation definitely has changed. Okay, our expectation is either things happen before or things happen after. So 1251 is the total number of deaths. They can either happen before or they can happen after. So we just divide it by 2. And that will give us around a value of 652.5. Okay. Now we still do the chi-square test because we are still testing for, so this essentially is still a test for association. Okay, there's one more thing. Okay, so we're going to work with the directional alternative in this case. Okay, so the directional alternative is something which we are interested in, that more number of people end up dying after their birth, right? So the directional alternate is more people die in, or more people in cluster 2. Okay, cluster 2 is where your birth month, the deaths happen after the birth month. Okay, so the chi-square is calculation remains similar, but it's very simplified now. So we are going to essentially just work with two values now. And similarly for the other, which is 691. Okay, and if you calculate, the value that you get is 15.38. Any guesses as to what the degrees of freedom would be for this particular chi-square term? Yeah, so that's right. So 2 minus 1, right? So what is really happening here? So what have we done in this entire process? So in the entire process, between the difference between what we were doing in A and B is essentially trying to look at a different, completely different paradigm of looking at the problem. In problem A, we were looking at the association between the birth month and the death month independently, in some sense, essentially looking at how different is how is there any association between the birth month and the death month, which could be in any of these 12 categories. In the second problem, we have become more focused and we are looking for association between the birth month and the death month, but in just two categories, whether that death month happens to be before or after the birth month. Okay. So the degrees of freedom are very less. Okay. And if you look up this value on table 9, which is down here, in table 9, 15.39 is going to be beyond this value, right? So 15.39 is going to be here, which essentially tells us that the two-sided p-value, so p two-sided, is less than 0.01. What we were doing, however, here in the problem was one-sided, right? So our alternate is one-sided. That essentially implies that p is less than this value. So at alpha equal to 0.05, we reject H naught or the null. However, we did not reject we failed to reject. Okay, so what's going on, right? So we are still solving the same problem. We are still working with the same data. In part A, when we were looking for difference between the birth month and the association between the birth month and the death month, we failed to reject the null. And in this case, by looking at the association between before and after, we now can reject the null, right? So what's really going on? So what's really going on essentially is that if you do this experiment, or if you ever work with any hypothesis in real life, the hypothesis is chosen beforehand, right? So you need to be essentially very sure about what association is it that you're going to test, right? So ideally, this association in part B is something which is probably more interesting to test rather than a very general hypothesis, something like which is in part A. So in part A, the hypothesis is very general, right? So we are testing between one birth month and the other 11 possible death months. In the second hypothesis, in the second scenario, we are testing for whether whether the death month happens to be before or after, before actually the birth month, right? So that essentially is a completely different hypothesis that we are testing, and hence it's a very different way to actually look at the data. So there's nothing wrong about it. The only thing that you need to be essentially understand from this problem is that in real life, you will choose what hypothesis you're really going to test. It can never happen that you can do both these tests and then choose, that part B seems to give me significance, and hence I'll choose that hypothesis to go with. Before doing any test, you actually essentially narrow down what hypothesis you're going to test. Okay. Okay. Any questions there? All right, so we'll move to problem 3, which essentially is in some sense a generalized version of what we did for the what we did for problem 2. In this case, we are essentially given what's called a contingency table. So a contingency table is essentially, so what is a contingency table, right? So contingency table is essentially in some sense a row versus column of two different categorical variables. Okay, that's the definition of a contingency table. So here we're given 2 cross 4. Okay, what does that mean? So we have 2 rows and we have 4 columns, right? Now, what are the categorical variables here? So the categorical variable here is the row is the sex of the dog, and the column is the color of the coat. Okay, so this is essentially a contingency table with 2 rows and 4 columns. What is that we are interested in? So we are interested in testing whether there is any association between the color of the coat and the dog's sex. Okay, again, so moment you see this word of association, just think about the only test you really need to really worry about is the chi-square test. Okay, how do we do the chi-square test in this thing? So in any setting of chi-square test, we require an observed and an independent variable. An expected variable. So we have the observed values definitely here. We need to come up with a way to find out what these expected values will be. Okay. Any guesses as to how do we come up with the expected values here?
Isn't it the row times column divided by total?
Perfect. Yes, that's right. Okay. So this table is essentially given in an expanded form here. So you're given the rows, you're given the row sum, which is 450 for males, for 550 for females, and similarly, these are the corresponding column sums. Okay, so how do we come up with the expected value? So let's look at for male and black. So the male and black, essentially, in some sense, what you're saying is the value of the expected value of the a dog which is male and black is given by 450, which is essentially your row sum, times the column sum, which is 328, and it's essentially normalized by the total count values you have, right? So make sure you understand that this value is almost always actually always going to be less than 1, right? So this is always going to be, this is always going to be in the range of what you're essentially getting. So the final sums that let me back that up. So the final sum values for, if you do this operation for all the values for white, gray, and spotted, then the final sum that you get here will again be 450. Okay, there's no surprises there because you're essentially in some sense working with the ratios here. Okay, so I've already cheated a bit and I'm giving you the values, the expected values for all of these tables here. So if you sum up these 4 values, then they should sum to 450. That should be a quick check. Okay, and same holds for the column-wise summation as well. Okay, so we have the expected values here. So how do we do the chi-square test, right? So again, in order to do the chi-square test, we are going to work with the expected values here. But before we do that, we need to answer the first problem, which is how much, what is your null hypothesis, right? So what is a null? So there is no association between the color of the coat and the sex of the dog. What does it mean to say in words? Sorry, in symbols? So there are multiple ways to think about this, right? So one way to think about in terms of symbols is the probability that I get a male dog, given that the coat of the dog is black, is equivalent to me getting a male dog if the dog is white colored. Okay. Or similarly, you can say this for female. And you will expand this to essentially cover all the other coat colors, which are gray and spotted. Does everyone understand what I'm doing? So the probability that I get a male, given that the color is either black, white, gray, or spotted, is essentially equal in all the 4 categories, right? Why is it equal? Or alternatively for the female. So what this essentially means is there is no association, and hence if I'm coming from any of these 4 categories, which is essentially my color, then either the probability that I get a male is going to be equal. Okay, you can again also flip these. So you can also exchange these two and condition it on being a male, and that's essentially equal, right? Does everyone understand what I'm trying to say? So there's no association. There are 2 categories. So there are only 2 possibilities that could happen for, so there are 2 categories for male and female, right? So there are only 2 possibilities that could happen. The first way to write this is that the probability that I get a male coming from any of these 4 categories is equal. The other way to write this is the probability of being a female coming from any of these categories is equal. You can also switch between these two. What this essentially means is the probability of being a black, given that I'm a male, is equal to probability of being a white, that I'm a male, and so on. Okay. Okay. So next we are asked, what is P black given that I'm male? Okay. So this is something that I need from you. So how should we answer this? What is P probability of being a black given that you're a male? Any guesses or any answers? You have done this in your previous part, right? So you've done this when you gave your exam 1. You've seen a very similar problem.
Is it 158 over 328?
Okay, let's see. So this is what? We are black and male, and we are male. Is that right? Okay. So what is the probability that we are black and male? So let me use a different color. So we are black and we are male. So that's 158. And we are male for sure, right? So if we are male, that's 450. Does that make sense? So this is black and male, and 450 is that you're male. So that's 158 by 450. Okay, and that is 0.351. Okay, so make sure how we reached here. That's something that you should understand. So the probability of being a black and male. So this formula we know by now, right? So probability that you're black given you're male is the probability that you're black and male divided by the probability that you're male. So the probability that the dog is male is the total number of, so if you want to be more explicit, you can write this in this form. This is actually the probability, right? But the 1000 term gets cancelled. Okay, everyone understands this part? And if you do understand, let's try to solve what is the other part, which is that your male given the dog is spotted. Okay, how do we get this? So male and spotted. So this and spotted, right? So that's this. So this is going to be 46 by 93, and that's close to 0.5, which is 0.494. Okay. And the reason for asking you to calculate this value is to give you a sense of how close are these values, right? So how close are these values to the expected proportion at all? So what do you expect in terms of if you believe that, let's use a different color. So if you believe that this fact is true, then what do you expect this proportion to be? What should this be equal to? If the null is true, that's your null. What should that proportion be equal to? So it's slightly tricky, but if we assume that if the number of black, white, gray, and spotted dogs are equal, and we expect all of the condition probability of the male being equal in all the cases, then this is approximately equal to 0.25, right? And this is assuming same number of dogs in each coat category. So if you don't understand this part, that's fine. It's something that's not really required. But I just wanted to give you a sense of what is it that we are really expecting from this problem, right? What is it? What is our actual null expectation? So if the number of dogs in each category, if the number of black, white, spotted, and gray dogs are equal, and we are assuming that there is no association, then we expect this proportion, all of these values, this probability value, this, and this to be equal, which is going to be equal to 0.25 because all of them essentially sum up to 1. Okay, so if we want to do a test for association now, right? So what would we, before we do a test for association, we want to be able to do problem D. So the number of the degrees of freedom are given by R times C minus 1, right? So this is essentially the number of rows. This is your number of columns. This is 2 minus 1 times 4 minus 1, which is essentially 3. Okay. And finally, we're going to calculate our test statistic. Okay, so you're given the expected values here. The expected values are 147.6, and what we saw here was 158. So 158 minus 147.6 square plus 209 minus. Okay, and if you calculate this for all the 8 terms, you'll get 4.7048. We know the degrees of freedom, which is 3. So we go to table 9. Okay, so table 9, degrees of freedom equal to 3. I'm going to look for 4.08. Sorry, that's the 4.70, right? So it's going to be somewhere in between 4.7. Okay, so a p-value for this problem is a number between 0.2 and 0.1. Okay, and hence at alpha equal to 0.05, we fail to reject. H naught. Okay, so we do not find enough evidence to claim that there is association between these two categories. Okay, in some sense, what essentially we are saying is there's not enough data points for us, or there's not enough information for us to claim that there is indeed an association between being a male and being a black, white, gray, or spotted dog. Any questions so far? Anything that's tricky, anything that's not clear, I'll go over it again. If not, I'll quickly go over some of the review problems that are designed for the exam. They're very simple, but might help to just go over them together. I might not have time to solve all of them, so I'll just give a quick rundown of how to do it. The solutions are going to be available on the Blackboard, but before you see the solutions, I'll encourage you to try these review problems on your own. Okay, that's how they're designed to be. But all of them are very simple, so I'll just give you a quick overview. But before I do that, any questions about chi-square test? Any questions about any of the other tests that we have talked about? Any questions about the exam? If any of you are facing any difficulty because of the ongoing situation and you want to talk, please feel free. My office hours are still on Tuesdays, 3 to 5. If that doesn't work for you, please feel free to email me, but just don't shy away. I know the times are slightly tricky, but are you going to post the answer keys to the most recent quizzes? Okay, yes, that's a good question. So I'll post the answer key to the quiz, the previous quiz, yes. And the quiz before that as well, because I did not have chance to return that to you. Okay, cool. Any other questions? Okay, so we're almost out of time, but let's quickly go over problem one. So problem one essentially gives you the mean and the standard deviation for, again, a control versus a treated group setting. And let's first treat the problem. So the study was the pain score that each are reported on a scale of 0 to 10, 4 days after the surgery. Okay, so what is the standard error for the mean of the coblation surgery? So somebody is conducting a surgery and they're comparing the conventional to a newer procedure. So before we get started, what do you think is this setting? Is this paired? Is this unpaired? Paired, unpaired? Think about it. It's not given in the problem. Yeah, perfect. So it's going to be unpaired, right? So you don't even have to do anything actually. You just look at the number of samples here and they are different. And you also think about it a bit more closely, then you'll think about nobody is going to actually do two surgeries at once, right? Once you do the surgery, your expectation is that you've actually cured the patient. So this is unpaired, right? And then how do we calculate the standard error? So the standard error for unpaired setting is very simple. You just take the square root of the summation, okay? And you know what this standard error is going to be. Standard deviation by the by n, right? So square root of n1 and square root of n2. Okay, 95% CI. I'm sure by now everyone knows how to do that. So I'll skip that. Okay, the effect size. So the effect size, I'll take problem E. So what is the effect size? So effect size is essentially given by y1 minus y2 bar upon the standard error of y1 bar minus y2 bar. Okay, so this is your standard error of y1 bar minus y2 bar. Just plug in the values and you'll get the effect size. What are the conditions? Let's go to problem two. Conditions for validity of t-test. So you require normality, you require SRS, and you require the two groups to be independent, okay? And in some sense, this kind of is part of actually SRS. So this is not a hard and fast rule. It requires a large sample size, and this large is a tricky number to decode, but generally 30 plus is a good number, okay? but in some cases, even something like 10 is good enough. Wilcoxon-Mann-Whitney should be preferred over t-test. When should you prefer, right? So this is a non-parametric test. This is a parametric test. This is in general more powerful. The t-test is generally more powerful. But when would you prefer it, right? So very simple. Normality not satisfied. Okay. Or if you have small sample size. What is the difference between Wilcoxon-Mann-Whitney and Wilcoxon-Sign rank test? Okay, so that should be simple. What is the difference? So we have working in paired versus unpaired setting, right? So one of them is paired, while the other one is unpaired. So which one is more powerful? Wilcoxon-Sign rank test is almost always more powerful. Okay, I'll leave the remaining 3 questions for you to solve. The solutions will be available, but if you have any questions, please let me know. The way these review problems are designed is for you to solve, but I just wanted to quickly go over some of them so that there are no confusion. Okay, but if you have any questions about any of these review problems, just please feel free to email me. I'll also post a review sheet, so you should be able to, in principle, go through that review sheet. It's going to be very similar to what we did before the previous exam. So all of these notes will be available as one document. I'll do that shortly after this. Okay. Okay, with that, good luck. I know it's going to be a different exam, but you'll have enough time to solve that. Let's have a question. Okay, cool. All right, if there are no questions, I'll let you go. If there are any questions, I'll stick around for a couple of minutes. You can ask me right now, or if you want to hang up, then you can just email me if you have any questions. Okay. Okay, cool. Any questions, Lauren? Yes. Any questions, Lauren?
No, I'm okay. Thank you.
Oh, okay, cool. Thank you.
Okay.
Yeah, bye.